Operating systems are the unsung heroes of our digital lives. They act as the intermediary between us and the hardware of our computers, managing everything from memory allocation to program execution. Without operating systems, using a computer would be like trying to speak a foreign language without a translator. Difficult and frustrating. Operating systems come in different flavors, each with its own structure and approach to managing system resources. Understanding these structures is crucial for comprehending the strengths and weaknesses of different operating system designs. In this essay, we'll delve into three fundamental operating system structures: monolithic systems, microkernels, and exokernels. We'll explore their inner workings, weigh their advantages and disadvantages, and gain a deeper appreciation for the complexities of operating system design. By understanding the core principles behind these structures, we can better appreciate the ingenuity that goes into building the software that powers our digital world. The simplest and most traditional operating system structure is the monolithic system. In this design, all operating system services, from file systems to device drivers, reside in a single large kernel space. This monolithic kernel runs in supervisor mode, giving it unrestricted access to all hardware resources. Imagine a monolithic system like a one-story house, where all the rooms, the kitchen, living room and bedrooms are directly connected without any separating walls. This design makes communication between different parts of the operating system straightforward and efficient. However, this simplicity comes at a cost. Because all operating system components share the same address space, a bug in one component can potentially crash the entire system. Furthermore, adding new features or fixing bugs often requires recompiling the entire kernel, which can be a time-consuming and error-prone process. Despite these drawbacks, monolithic systems have been widely used in operating systems like Linux and Unix due to their performance and ease of implementation. The tightly integrated design allows for fast communication between system components, resulting in efficient overall operation. In contrast to monolithic systems, microkernels and exokernels adopt a modular approach to operating system design. They aim to improve reliability and flexibility by dividing the kernel into smaller, independent components. A microkernel, as the name suggests, contains only the essential functions of an operating system, such as process scheduling, memory management, and inter-process communication. Other services like file systems and device drivers are implemented as user-level processes called servers. These servers communicate with each other and with user applications through message passing. Think of a microkernel system as a house divided into separate apartments. Each apartment represents a different operating system service, and communication between apartments happens through a central mailbox system. This separation reduces the impact of a single component failure, as a crash in one server won't necessarily bring down the entire system. ExoKernels take this modularity even further. They provide an even smaller core of functionality, focusing solely on resource protection and multiplexing. ExoKernels delegate most operating system tasks, including memory management, to user-level library operating systems, libosses. These libosses can be tailored to the specific needs of applications, allowing for greater customization and flexibility. While microkernels and exokernels offer improved reliability and flexibility, they also introduce performance overhead. The constant message passing between components can slow down the system, especially for tasks that require frequent communication. Choosing the right kernel architecture for an operating system involves carefully weighing the trade-offs between performance, reliability, flexibility, and complexity. Monolithic systems excel in performance due to their tightly integrated design, but they suffer from potential instability and difficulty in maintenance. Microkernel systems, on the other hand, prioritize reliability and flexibility by isolating operating system components. However, the message passing overhead can impact performance, especially for communication-intensive tasks. ExoKernels push the boundaries of modularity even further, offering unparalleled customization and flexibility. However, their complexity and potential performance limitations make them more suitable for specialized applications, rather than general-purpose operating systems. Ultimately, the best kernel architecture depends on the specific requirements of the operating system and its intended use. Understanding the strengths and weaknesses of each approach allows developers to make informed decisions and build operating systems that meet the diverse needs of our increasingly complex computing landscape.